Hi everyone, thank you for coming to our session. I know this is the last session of this year's Black Hat, and I really appreciate that you can listen to our talk. So today's topic is the container security. It's the cloud-native sandbox for microservices. So at the very early beginning, I want to spend some time to introduce ourselves. And currently, I'm a chief AI security scientist at JD.com. And JD.com is the largest e-commerce company in China, and it went to public at 2014, and in 2017, we have more than 1 billion active customer. And since we have a lot of the customer data stored in our cloud, so we put a lot of efforts on the cloud security and design and deploy some state-of-the-art tools to make our cloud secure. And my research topic covers from the container security and the IoT security as well. And I also regularly share my research to the security community by talking about them in the conferences like Black Hat and WebB.
Hi everyone, my name is Zhao Yan, and I'm currently working as a principal security researcher at Palo Alto Networks. And gladly, I have some cooperation with Tom Bo in this project, working on some container security stuff. And the Palo Alto networks also are producing some new roadmap for the container and cloud security products.
Okay, so in today's presentation, I will start with some introduction about container security, and then we are trying to to share our motivation, like why we want to design and implement the container native sandbox. And then I will want to try to explain some key design questions that we are facing during our research, and then I will try to explain the parallel execution and the alignment analysis we designed for the container native sandbox. If we still have time, I want to show some case study to just show how our sandbox works. So the container concept, so it's a very hot topic in the past few years. I think most of the people here have already used container or Docker in your daily life. It's just built based on the namespace and the C group concept in the Linux. And because the feature of the container, people use the cloud native and the container based cluster. So they will just deploy their microservice on this cluster like the normal cloud. But in order to help the DevOps team to deploy and manage their microservices, and the orchestrators was designed for that purpose. And the most dominant one in the current market is Kubernetes, which is developed by the Google. And from the security perspective, a lot of security researchers trying to study the container security, mostly focus on two aspects. The one is trying to focus on the image vulnerabilities. They are trying to figure out, given an image, how many vulnerabilities could be in that image, which is which is not hard to do, because they can just extract a file from the image and then they know the exact software and the version installed in that image, and then they will compare it to the CVE database, and they know exactly that number, like how many vulnerabilities could be in that image. And as the previous study shows, that the number of vulnerabilities in the image from the Docker Hub has increased year by year. And the other researchers trying to find the vulnerabilities in the Docker runtime or in the Kubernetes itself, because those vulnerabilities are much more common. Because if the attacker can compromise one of the pod in the cluster, they can because nearly every cluster, they use the Docker runtime or the Kubernetes, so that they can leverage those vulnerabilities to take over the whole cluster. And most of the existing product on the container security, they are basically provide two features, either just provide some static image scanner or the dynamic runtime provision or detection tools. And so speaking of our product, so the motivation is more like, because we know the container for a while, we are trying to ask ourselves like how this new concept could change the landscape of Sandbox, existing Sandbox product. So the answer comes from two sides. From the problem side, it's more like because this container-based cluster is a quite new thing, and there's no such a novel sandbox tool specifically for this kind of cluster to discover container-based threats. And for the opportunity side, we are trying to rethink the design of traditional virtual machine-based sandbox. Say, if we can design a container-native sandbox, what we can achieve more than the traditional sandbox did. So there are two new cool features that we can provide, which cannot be done by the traditional virtual machine-based sandbox. One is that we can provide the context awareness-based detection. It's more like giving a container. We are able to just we can allow the user to upload their context. Like their Docker file or a Docker image along with their sample, so that we can reconstruct the exactly execution environment as the one that the user will actually open that sample in the real world. This cannot be done by the traditional virtual machine-based sandbox because the size of the virtual machine is too large. And the other one is that because the container itself is quite lightweighted, so that we can just using a limited resources to launch and run multiple instances of containers. Then we are able to just feed the user upload the sample to one of the container, and then feed the benign but similar sample to the other containers. Then we collect the behaviors, and then we just need to find the differences between the two behaviors, which allow us to pinpoint exactly the actions taken by the sample for the exploitation. And so in order to design a container-based sandbox, we have to answer these four questions. The first is how to make it convenient to use Sandbox in the container-based cloud. So the answer is we have to just integrate the Sandbox concept into the orchestrator itself. Taking the Kubernetes as an example here, we can just leverage the CRD things to extend the Kubernetes API. And by doing so, we can just introduce a new resource type called Sandbox to the Kubernetes. Then the DevOps team, they can just use the normal way that they managing the Kubernetes resources and use a similar way to manipulate or interact with our sandbox. So there's no learning curve, for the new users to our sandbox. For example, giving this YAML file, which is quite a standard way that the DevOps team use to create a pod, and they can just modify a few fields in the YAML file. Then they can just upload their sample as well as their context here. Then our sandbox CRD controller will just set up the environment and then just run the sample and do the analysis based on this YAML file. The second question is how to efficiently retrieve and build the context for the sandbox. So this is one of the main feature we want to provide in our container-based sandbox. And so because that is for the environment sensitive detection, so unlike the traditional virtual machine-based sandbox, the user will just upload the sample file along with the context. So the context could be uploaded in two ways. In the explicit way, the user, just like what I mentioned before, so your user can just upload their Docker file, Docker file or their image name, and based on those information, we will just try to reconstruct the execution environment. And this also can be done in the implicit way. It's more like this is very useful in the container-based cluster deployed using the orchestrator, because every container's information running in the cluster is managed by this orchestrator. Then, if we know, say, if the DevOps team they just point out one of the samples delivered in the traffic in the cluster, what we can do is that based on the destination, if the destination IP or those information, we can just directly get the information of the target container. Then we can just get all of the container information from the orchestrator. Then we can just reconstruct the execution environment. So in addition, we also need to provide the strong isolation, because the container itself it doesn't provide the hard or strong isolation, because every container in the cluster or in one host they just share a same kernel. So if there's a kernel vulnerabilities there, so the attacker could compromise the whole machine. Basically, they can jump out of the container sandbox. And there's multiple ways that we can achieve the strong isolation using the kata or the gvisor. Basically, what they did is that they just add another layer, like a hypervisor, underneath the container, so that they can achieve the same isolation level as the virtual machine. The third question is how to collect the sample behaviors in the sandbox, which is very important, but it's also a quite common problem, because every runtime detection tools, they are facing the same problem, and there are a lot of open source tools or libraries out there that you can use to collect the runtime information, like the system calls. And we use the C-stick, which is a very convenience tool that which help us to collect every system call from the invoked by the container. And so the last question here is how to analyze the sample behaviors beyond the existing detection mechanism, because like I mentioned, there's some unique feature of the container that the virtual machine technology doesn't have. So we want to leverage those unique features to provide something new that can be used for the detection. So what we propose here is the parallel execution and alignment analysis. So the idea of parallel execution is quite straightforward. Basically, we can just run two containers created from the same image in parallel, and then feed two samples. One is suspicious, one is the benign, to each container at the same time. Then, based on the collected information, we are trying to find the differences between the two behaviors. So basically, the idea is more like we are trying to reduce the noise, because not every actions taken by the sample is malicious, because the majority of the actions is just like quite it's a quite common thing that they need to follow the existing flow of the target software, and at a certain point they will trigger the exploitation, which is like a abnormal things. So comparing to the normal software, the behavior of the normal sample. So if we can find a different, we can just easily detect the malicious behavior. So in order to perform the parallel the alignment analysis, we have to just convert the raw data to a syscall sequence, which is also quite straightforward because we can collect basically every information regarding the system call. We just need to group them based on the container name and the PID. Then for each group, we just extract the syscall name, and then map each syscall name to a unique character, so that we can just generate a sequence of syscalls. We call this a syscall sequence. This seems quite easy, but during our research, we found out that in the real world, it's hard to just directly using this syscall sequence. The first is a performance issue, because you know that the number of syscalls generated at each second is quite large. So in our evaluation, we collect 1,000 to 5,000 syscalls per second and per process. If you just directly apply the alignment algorithm on them, we will just wait forever to get the answer. So the solution is that we need to filter out some unnecessary calls, which does not is quite common. It doesn't give us so many information. And then we just normalize the similar calls, but in the calls that have a similar functionalities to it together. And then the last step is that we just compress the continuous calls to a lower number here. So by doing these steps, we can just reduce the length of the syscall sequence to only 10% to 30%, which allow us to generate alignment result in few seconds. And another challenge is that it's a scoring function, because the quality of the score function is a key factor to determine the quality of alignment result. Given this two syscall sequence here, so they generated by the same kind of input or same kind of input pattern. The first, the microservices are in the idle stage. Then we just connect to them and then send a request. And by doing so, we upload the sample to them. Then the last stage is the sample execution. So if we run the traditional scoring function, if we run the traditional alignment algorithm with a traditional scoring function, we will get a result above. Obviously, this is the meaningless, because this cannot be used for the security analysis. Basically, what we want to achieve is the figure in the bottom, because we want to just align the syscalls in the same generated by the same stage together, and because the traditional score function is used for the biological purpose. Intuitively, they just want to match as many as elements in the sequence as possible, regardless the content of each element. So it's more like you just match some fraction controlled of your head to match another DNA sequence which is controlled your food. So although they from result it shows that they have a perfect match, but but it doesn't make no sense here. So in order to get our perfect alignment, we test a lot of methods, and in summary, we just believe that using this formula is have a most effective result here. So basically, the number returned by the score function is considered by three attributes: the how importance of the aligned say score. It's more like a certain. In the previous example, the the file related status codes here have a less important weight than the socket connection cost. So by giving the socket connection cost a higher score, we can just get a better result. And this importance weight can be calculated using the frequency of the sys call in the sequence. The more frequency this sys call happen in the sequence, the less weight for their importance. Similarly, also for the closeness, if we align the two sys calls that have a similar functionalities, we will get a higher score. And the last is the sensitivity. This is is designed for the security analysis purpose. The idea here is that for certain system calls that the security expert we believe that is very dangerous because it can be used for launch the attack. And then by giving them a higher score, we can just match those system calls invoked by the software itself. If we can match them out, so those unmatched sys calls, those unmatched critical sys calls could indicate the exploit. So at last, we also try our sandbox on various of our attacks, and then we are trying to answer: can we just pinpoint exactly exploitation fraction from the alignment, and then what kind of a unique pattern we can generate from the alignment result, which can help us to either create a signature or to for the forensics. And the first one here, so because due to the time limitation, so I may not go through the detail one by one, but you can we have a much more evaluation in our white paper. Please just read them if you are interested in the result. Basically, we try the path traversal here. The attack here is more like you will have a repeated block of file traverse steps from the alignment result. And then for the remote command execution, it's more like now we will just we can successfully align those common things which is processed by the software to pass the command, or it's more like a follow the binary path. Then at a certain point you will find out that there's a unmatched things. So a matched call for the fork or clone, which is basically is a exploit point by just running the inject command in the separate process. And so basically we try a lot of different type of remote command execution attack on different type of software. They all show the similar pattern here. Is quite obviously. So we believe that this can help the security researchers to further understand how the attack works. So so there's like I mentioned, due to time limitation, I can now just finish all of them. But so if you still have questions, please ask us offline, and again, thank you for coming to our talk. Thanks.